Hello again. In this part, we are diving into section C, which focuses on deep learning concepts. Here, we move beyond traditional machine learning concepts to understand the hierarchy of artificial intelligence, where deep learning sits inside machine learning, utilizing neural networks with many layers. We will break down the conventional neural networks, which is CNN, revolutionized image classification, and how recurrent neural networks, which is RNN, and LSTM handle sequential data-like language. We'll also touch upon fascinating architecture like GAN, which is generative adversarial network, where two models compare to create realistic fake data. Let's go through these advanced architectures step by step. Welcome back, everyone. So in this part, we will cover section C of our internal assessment 2 of data science, which focuses on the core deep learning concepts. Let's go through each section one by one with clear explanations of each one. Question 26. Deep learning is specialized subset of machine learning. After answering, it's crucial to understand the hierarchy of this system. So artificial intelligence is the broad umbrella. Inside that is machine learning, which are algorithms that improve with the data. And inside machine learning is the deep learning. Deep learning is distinct because it uses artificial neural networks with many layers, and hence it is known as deep learning to learn representation of data automatically. Whereas traditional or ML models often require a manual feature extraction. 27. Neural networks are universal approximators of the functions. This refers to universal approximation theorem. It's a mathematical proof which states that a neural network with just a single hidden layer, if it has enough neutrons, can approximate any continuous mathematical function to a desired degree of accuracy. This implies that theoretically, neural networks can model any relationship in the universe, provided that we have enough data and computing power to train them. 28. A network with more than one hidden layer is termed as deep neural network. A standard neural network consists of an input layer, hidden layers, and an output layer. If there is only one hidden layer, it is called a shallow network. The moment we add any second hidden layer, the network's technically considered deep. This depth allows the networks to learn hierarchical features, uh, which means simple shapes in first layers and complex objects like faces or cars in the deep layers. Question 29. Each layer's output becomes next layer's input. This describes the forward propagation process. Information flows in one direction. Layer 1 processes the raw data and spits out numbers. Layer 2 takes those data as input, processes them further, and passes them to layer 3. This chain continues until the final output layer makes a prediction. If the prediction is wrong, the network sends a signal backward, which we term as backpropagation, to fix the mistakes. Question 30. CNN are mainly used for image or visual classification. CNN, which is convolutional neural networks, were designed specifically for grid-like data such as images. Traditional network flatten an image into a long line of numbers, destroying the spatial relationship, which is data noise above a mouth. CNN uses filters to scan over the image, preserving these special patterns. This makes them the industry standard for computer visions like face recognition and machine imaging. 31. RNN handle data with strong sequential or time dependencies. Standard network engine data are independent. That is, image A doesn't depend on image B. However, in language or stock markets, the order matters, which is not good versus good not are both treated as the different entities. Now coming upon RNN, which is recurrent neural networks. They have a memory loop that allows information to persist. They take the output from the previous step and feed it into the current step, allowing them to understand context over time. 32. RSTM is an improvised version of a recurrent network, which is RNN. Standard RNN suffers from vanishing gradient problem, which is they tend to forget information if the sequence is too long. That is forgetting the beginning of a long sentence. Let's talk about LSTM, which is long short term memory. Networks fix by introducing gates. These gates can be forget gate, input gate, output gate, etc. These regulates what information should be kept and what should be thrown away. This allows them to remember long-term dependencies even in the cases of long chain of information being processed. Question 33. In a GAN, the second model acts as discriminator, distinguishing real and fake data. GAN, which is Generative Adversarial Network, consists of two models fighting against each other. These two models, first one is the generator. This tries to create fake data like a deep fake photo to fool the opponent. And the second one is the discriminator. It acts like a police officer. It looks at the image and tries to classify it as a real or fake. So these two entities, which are the generator and the discriminator, they improve together. As the discriminator gets better at spotting fakes, the generator is forced to create better fakes. 34th, reusing a pre-trained model for a related task is called transfer learning. Transfer training is a deep model from scratch. Sorry, training a deep model from scratch requires massive datasets and delayed of GPU time. Transfer learning takes a model already trained on a huge dataset, like ImageNet with 14 million images, and fine tunes it for a specific small task, like if you want to classify 100 photos of a specific product. And this method actually works because the model has actually learned how to see basic shape and textures. Question 5, 35, and 36. The wide part of wide and deep model helps memorize, whereas deep part helps captures more general or abstract features. This refers to wide and deep learning framework, which is popularized by Google for recommended systems. So in this wide and deep model, wide component uses linear models to memorize specific patterns that occurred in the past. That is, if, for example, in a commercial app system, a user bought item B. So it is precise, but it cannot handle new or unseen combinations very well. So in the deep component, this uses deep neural networks to generalize patterns. That is, for example, spotting a pattern in a movie recommendation system, like users who like scientific fiction often like tech gadgets. So combining these two components give us the best of both worlds, specific relevance and broad generalization. Question 37. Linear classifiers combines inputs with weights and bias to perform predictions. The fundamental building block of both linear regression and neural networks is linear equation. In this, weights determine the importance of each input feature, whereas bias allows the activation function to be shifted left or right. This ensures that model can fit data that doesn't pass strictly through the origin, which is 0, comma 0. Question 38. Activation function introduces non-linearity in the neural models. So this is a very good question. So if we stack multiple layers without activation functions, the whole network mathematically collapse into a single linear regression model, which is to learn complex curvy non-linear boundaries like separating red and blue dots arranged in a spiral. We need non-linear functions like ReLU, which is rectified linear unit or sigmoid applied after each layer. 39. Adding neurons or hidden layer increases model capacity. Model capacity is a measure of how complex a relationship the model can learn. A small model has low capacity. It means it can learn only simple lines. Whereas a huge network has high capacity, which means it can memorize the entire encyclopedia. However, higher capacity brings a higher risk of overfitting if we don't have enough data to support it or train it. Question 40. Transfer learning leverages retained or general features learned from prior tasks. So in deep learning, the early layers of networks, which is layer 1 to layer 3, acts as feature extractors. They detect universal features, which include vertical edges, horizontal lines, corners, and simple textures. These features are useful for every almost any visual task. Transfer learning freezes these early layers around and returns the final layers, saving massive amount of time and computational resources. So we have finished up with the section C of our internal assessment 2, which covered the DH concepts. Now we are left with the final section of our internal assessment 2 of data science, which covers the data structures of the in the Python, which we'll cover in our next video. Until then, take care. That brings us to the end of section C. We have seen how neural networks act as universal function approximators and how adding these in our model helps depth allows them to learn hierarchical features. From the wide and deep framework used in recommendations to the time-saving power of transfer learning, these concepts represent the cutting edge of the artificial intelligence. Remember the role of activation functions because without them, even a deep network is just a linear regression model. So mastering these distinctions between CNN, RNN, and GAN will serve you well in the exam. Now let's look at the code structures that make them possible in the section D of this assessment.